Okay, let's begin. We started last time to discuss the influence quantum gravity on conformal field theory. And basic points were, well, that we had several different approaches to this problem. One is to describe gravity in a conventional way, Einstein-like way, where the basic variables are metric tensor, G, A, B, and couple in a prescribed way, couple this metric tensor to the matter field. Say we can visualize the Ising model, or which is the same free fermions, coupled to gravitational field. And then the scheme of what we do next is that we calculate back reaction. We assume that this gravitational field, it carries, it fluctuates, and because of that, it changes, obviously, can change, let's say, critical exponents, etc. More concretely, what we did was the following. First of all, we calculated the polarization operator, which is given by the diagrams like that. We have a graviton here coupled to the matter field, whatever it is, and it is this Feynman diagram, like photon mass in quantum electrodynamics. Basically what the physical meaning of a polarization operator is the following. You take a system, you impose it, you impose it to some infinitesimal metric, and you calculate the reaction. The conjugate variable to the metric is energy momentum tensor, and basically we have this relation. And if everything is small and perturbative, then we just say, okay, that simply means that the gravitational field induces, if it is present, it induces energy momentum tensor. Analogously, if you have a quantum electrodynamic variation of the electromagnetic potential, would induce some current, which is conjugate. And the next step is, of course, in both cases, to take into account this polarization. It's a physical phenomenon. So, meaning that on the right-hand side of the Einstein equation and of the Maxwell equation or any other equation, you have to substitute not simply the original energy momentum tensor, but add this piece, the induced. So you have to add the induced energy momentum tensor. That's basically the prescription which is used in when you have dielectric, for example. Then an insulator, you calculate the strength of the Coulomb interaction, and it is actually you get a dielectric constant as a result. So that was the basic strategy. We had to calculate this thing. Maybe before I continue reminding you this, all that we, in some different words, we already discussed. I just want you to understand the more formally. It's a brief digression. Let's understand more formally why we should substitute the total current and what it current corrected or tensor energy momentum tensor corrected by vacuum polarization. I will simply remind you that in QED we have integral over a mu. We have f mu nu square, and we have w of a, which is w of a is the logarithm of the fermion determinant. So the w of a is integral d psi, integral psi, psi, and I remind you that diagrammatically w of a is something like that. So the suggestion which I just made, simply take the consider it as a correction to the current and to electromagnetic current in this case. It will be correct in this naive form. First of all, provided that these higher nonlinear terms are small enough, so it's a weak field expansion. Now, it also basically the suggestion which I made it boils down to replacing the original Maxwell equation by the equations of this type. Now, what kind of approximation? It's not an exact equation. If you want to solve, although it will give you these polarization corrections which we're considering. So my question is, when, under what condition, and what it really means that we take, we solve classical equation simply corrected by this extra term, which is the induced current. Actually, the induced current is just variation with respect to a mu. And this current depends on A, of course. And so we are writing the equation and get some, if field is small, we get simply renormalization of charge, but if it's large, we get nonlinear correction. Maxwell equations become nonlinear. But that's not my question. My question is actually quite simple and trivial. What kind of approximation is made here? It's not an exact equation.
It's not exact quantum?
Yes, in quantum electrodynamics, it is a certain approximation. And what kind of approximation?
It's just solution for an equation for classical.
That's right. Actually, if you look at the operator, this is exact in terms of operators. Now, if you have this equation, this quantum equation, we can take matrix elements. So we take the expectation value of f mu nu, and it will be this will be the correct exact equation, which you how would you derive it, by the way? This is an exact equation, and actually what I wanted to say that it's the approximation. It's approximately equal to J nu induced when you replace this quantum field by its average. Then you get this prescription. Then you indeed, but it's actually quite easy to figure out when it is correct. Indeed, the point is that we obtain this quantum exact equation by simply, or we can obtain this equation. How would you formally get it from the functional integral? Well, something more concrete. How to get the equation? You are given this.
Consider classical variation over.
That's right. Actually, you have to. It's like you derive. It's basic reward
like
identity.
Schwinger-Dyson.
The what?
Like a Schwinger-Dyson.
Yes. So you simply vary a, change variables a mu to a mu plus delta a mu, like you do when you derive word identities. This is, and then you get precisely the equation written here. This equation, and then the approximation made to when we introduce dielectric constant or magnetic permeability, the approximation is that you replace, you neglect higher order fluctuations, which in terms of Feynman diagrams basically means, what do you think, which type of diagrams are neglected when you replace quantum expression as function of photon by classical? Loops, photon loops is what is neglected. Now the last comment in this digression is that there are circumstances, that's in QED, generally speaking, this is unjustified. However, you can always look, and that usually gives you a good orientation. You can, how would you modify QED so that this becomes a good approximation and have a parameter which makes it better and better?
Add flavors.
Yes, add flavors. And the answer, as you probably know, if you have many flavors, then the field A comes from large number of sources, and by the law of large numbers, its fluctuation is suppressed by 1 over square root of n, and that's why you can use this thing. Usually, it gives a good picture. But replacing this, neglecting these fluctuations. Anyway, what we found last time was that when we find the effective action for the gravitational field, yes?
In other words, it means that you can apply a mean field.
Yes, exactly. Remember when we derived the mean field in the Ising model, we did precisely the same type of replacement. And basically for the same reason, because it was justified in the Ising model in the limit of when one spin interacts with many neighbors, long-range interaction. And it's the law of big numbers which is responsible for this approximation. Well, we found the propagator. We used the light cone gauge H++. We found the propagator H++, which was proportional to Q plus to the cube divided by Q minus. And with this propagator, we calculated corrections to this, and there's 1 over C, which is C is the central charge, and we found logarithmic corrections. And then I simply said, but didn't really prove anything. I said that so when we have fermion, the green function, what we found is that the green function is 1 over p hat, 1 plus 1 over c logarithm of lambda squared p squared plus etc. Then I said that these guys exponentiate, and as a result, the original anomalous dimension, which was normal dimension, and the isomorph free fermions, they had normal dimension, 1/2. But it becomes modified by these exponentiated logarithms. That, unfortunately, I don't have time to go into the details, but that can be solved. This problem can be solved exactly. What can be solved exactly, once more, is precise summation of all terms. It appears there is some symmetry in the problem which allows to solve it, but that we will not go into. Partly because this method is, it was quite fascinating in this particular set of problems, but for more interesting cases, so far it didn't solve the problems in more complicated, beyond minimal models. It's probably when something like that should be developed in ADS, CFT, etc., but this didn't happen yet. Okay, so we found this anomalous dimension, and there is one point which, again, I have to discuss before moving further, which is that we are dealing with a particular gauge, and the question is, what are observables? I told you before that in quantum gravity, if you have a field, any field, phi, be it boson or fermions, this is not a gauge invariant quantity, because under gauge transformation, this function changes that we already encountered with. So what are real observables? In other words, you can say, okay, we calculated the correction to the green function, but what's worth of it? Maybe it's just an artifact of the of gauge invariance. It's just some gauge artifact. In fact, it's not, because let's think of what kind of quantities are we can really discuss in quantum gravity. If you have some operator, A of x, the first thing which we can calculate is its expectation, is the invariant it's not gauge invariant, but if you take square root of g, if a scalar operator, A of x d dx, this is invariant, but this is a number. So you can, one thing which you can calculate, let's call it A, when you have many different operators, it was without gravity. Without gravity, we had operators O n. Well, it's not good. I use letter psi here. O n of psi. But with gravity, the correlation functions themselves are not physical. We have to calculate correlation numbers, not correlation functions. And these correlation numbers really give you information about about geometry of the system. We can use this calculated anomalous dimension to conclude, for example, that the free energy of this system will scale as a cosmological constant to some power alpha. And this alpha is related to this anomalous dimension. And so what is free energy? It's basically you take mu A and take the so in general you introduce the set of numbers with gravity. So with gravity, and you study the following thing. You introduce the coupling constant and you study their expectation value. And that gives you, and then you can apply the dimensional analysis. If you know anomalous dimension of ON, you can apply it to conclude what kind of dependence you have on these lambda n's. And that's basically, we will now come to this from the totally different angle, from the discrete gravity, and we'll see that continuous gravity and discrete gravity coincide in a sense. But that, before I come to this, once again, we have correlation numbers. We have also something else, but it never been effectively calculated. The other type of observables, namely, you can have have conditional expectation value. A bar is expectation value of this operator, and as I said, it generalizes to this, and you get e to the f, and it actually, that's all questions you are allowed to ask about the system, namely the expectation value or the expectation value of the averages. But now there is conditional operators. You can define A with condition that B has certain value by the following formula. You simply have d xi square root of g, a of xi, delta function of b minus b of xi. And this is another type of, so this is, the meaning is that you measure the value of some operator under condition that a different operator has particular chosen value. And that's slightly more sensitive than this simple average of A.
Why should we integrate over all space? Because we have different dimensional layers.
Yeah, we are doing it because we have no other choice, basically. And if you simply, in fact, well, first of all, why we are doing this? Because that's the only way to get coordinate independence. That's the only way you have gauge independence. See? Otherwise, in quantum gravity, it's not clear what we are doing. actually, this thing is slightly improves the situation, because you can always say that you have some field. We can, for example, we can have 4 fields if we are in 4 dimensions, and we can calculate A provided that BI's are fixed. And you see BI's play, it's analogous to coordinate fixing. In fact, you can show that in the semi-classical approximation, in some classical approximation, you can choose BI so that A will be a function of coordinates. Because what I'm trying to say is a highly non-trivial question, which is not completely clarified in the literature. Namely, what can we really measure in quantum gravity? And you can, the natural question you can ask immediately. So all these contortions with integration over psi and so on, why we don't need it in general relativity, in classical general relativity? In classical general relativity, we solve Einstein equation for the black hole, and we get the answer which depends on coordinates, and we don't bother about these things. But in quantum gravity, these coordinates themselves are fuzzy, and you have to do something with them. And we basically learned a lot from this two-dimensional case and from the discrete gravity, which I'm coming to. We understand what really is measurable and what is not, and so on. And one last comment about that. And I don't pretend that I can exhaust the question. As I said, it's an unsolved problem. There's also one more interesting expectation value, which is gauge invariant and which can be calculated. We can ask the question, what is the correlation of two fields separated by some length L? I shall explain. Let's suppose that we take the following thing. And try as a first attempt. So we integrate over d psi 1, integrate over d psi 2, and we can. What would you suggest? This is just a product of the two things. What would you suggest we can? How can we define it to measure the correlation, or which depends on the separation of operators? Something conditional, some extra condition to make it, to make these operators being at some finite separation. Well, we can. Any suggestion?
Can we set delta function?
Yes, that's what I'm going to do. And as I will tell you a minute later, it's not a perfect solution, but we can modify it. So we can actually introduce the following: the function L, Xi1, Xi2, and G. G is the metric. So this is the minimal, we can define it as a minimal distance between points Xi1 and Xi2 in a given metric. Okay, and that gives us some a, b as a function of L, which we probably can interpret as a correlation function. Now, what I found, however, is that this is a not very convenient object. It has some more divergences than, well, quantum gravity has divergences, but we more or less understand where they come from. This has extra divergences, so it's not a good object, but it's clear why it's not a good object and how to improve this formula.
We can try to smear it.
Yeah, you sort of, yes, but what's, okay, make your suggestion. The smearing should have some good physical meaning. Well, you know, what I'm saying is that here we take class L, C1, C2, is integral of GAB dxi dxib, and we take it along the minimal path here. So it's a minimal distance, as I said. But that's inconsistent. We are actually dealing with quantum theory. So we should not be taking the minimal distance. We should be taking what? What would be the natural replacement of the minimal distance in quantum theory?
Just the e to the I action.
Yeah, it's exactly. We should take the sum over all possible paths, and that is nothing but if we have a sum over path psi1, psi2, which in the limit may become L. What do you think? What is this? If we sum over paths with a weight e to the minus mu L of psi1, psi2, and g. It's a propagator, so with a mass mu. So the observable quantity will be the following. It's a of xc1, b of xc2, square root of g and multiplied by the propagator which of a scalar particles which measure with a constant mu, which we can, after calculating, so physics will depend on mu. If we take Milin transform with respect to mu, you will return to the quantum version of this thing. The conjugate variable to mu will be the length, and so you will have some natural definition. And I checked long ago, it has much more reasonable properties than the classical thing. And you sort of measure the distance not by classical delta function, but by the quantum propagator. But it's still such things actually, even in 2 dimensions, have not been really calculated. But let me show you what has been calculated, and that's quite. Again, we started already last time. We started from doing this. All this apparatus, you can. There is a. Before I go to this discrete gravity, those simple expectation values, correlation numbers, now known in all minimal models. People calculated them, and they are non-trivial. They contain some. They depend on the type of operators, and they're highly non-trivial. But that's all information you are allowed to have in quantum gravity, modulo all these modifications, which has not been done. But it turns out that there are two alternative ways of calculating these correlation numbers. In a sense, there is a way to you see what ideally would be we would have to not to we got to them in a rather indirect way by introducing gravitational field in a certain gauge, integrating things out, and so on. Would be nice to follow the same route as we did in conformal field theory, namely postulate certain properties of these correlation numbers and develop some calculational scheme for. That's done to some extent, and I will explain to you why. There is quite remarkable that there is a totally different the way of calculating these correlation numbers. We will not introduce the metric at all, but we will calculate these numbers. So let me explain all this. And keep in mind, I repeat again, we're dealing with an unfinished subject. There are many open problems here, which are quite interesting, and I'm sure will be attacked in the future. Okay, so let's try to discretize gravity to avoid divergences and so on. In gauge theory, it's very simple to, well, it's simple, but not, well, but it still takes some. Let me tell you what kind of error how to correctly discretize gauge theory and how wrongly discretize gauge theory. That reminds me, I think there's a saying attributed to Niels Bohr, so that the expert is not the man who knows how to do things, it's the man who knows how not to do things. So let me digress again to gauge theory, and we have to Young-Mills theory. In Young-Mills theory, we have this expression for the field strength, and the Lagrangian is the same Maxwell-Lagrangian. It's trace of F mu square. Now let's discretize it. It would be good to have a discretization because things are divergent, basically, and so on. So let's discretize it by simply replacing d mu a nu by finite difference. A nu of x plus a is a lattice vector, mu minus a nu of x. Plug it in this, replace the integral by the sum, and live happy ever since. But it will not be very happy life. What will happen? This is a wrong way. And well, we lose it, but so we can say, so what? Maybe it's approximate in any case. And but when you try to calculate things, let me ask you a concrete question: will this theory be renormalizable? And if not, what kind of non-renormalizability will appear. So what do you think? If I introduce this type of discretization, I will get and go to the continuous limit. So I should say it more clearly. It's important concept to understand, so I shall repeat it more clearly. Suppose we cut off any gauge theory is logarithmically divergent, and it must be cut off. So it must be modified at small distances. Otherwise, it's just nonsense. Now we try this modification, and which classically is okay. If you now take a to 0, you will return to the continuous theory classically. Nothing dramatic will happen. Now we calculate quantum corrections, some loop diagrams with these new propagators, and then take a to 0. We will definitely obtain some logarithms and so on. Which are conventional, but the question is whether we can, in this limit, whether we can renormalize this theory, whether all divergences can be attributed to coupling renormalization and field renormalization. Why the Young-Mills theory is renormalizable in the first place? Dimensionless coupling, okay, but it's certainly necessary, but it's not sufficient. What else is, because we can obtain logarithmically divergent terms, renormalization means, in this case, that you can absorb all divergences in the bare coupling constant. Now, what do you think will happen if you simply do straightforward discretization like that? Well, what would happen is that, as you mentioned already, gauge invariance is lost. And so you will get not only these terms, but you will get, for example, let's concentrate on dimensionless couplings. You will get something like trace, counter term like trace a mu to the 4th, also with logarithmic correction. So you will get many terms like that, and therefore you started, the theory is not renormalizable despite, I'm not talking even about the fact that it will give you quadratically divergent mass for the photon, for the gluon, but suppose by dimensional regularization we can eliminate quadratic divergence. But logarithmic divergence would be pretty nasty. It will have, it will say, okay, you started with this Young-Mills action, but what you generated is not the Young-Mills action, but the action plus terms like that. So clearly you did a lot of damage to the theory. The right answer, which is to replace, to associate gauge field with the links of the lattice, and to introduce the unitary matrix. A is a Hermitian matrix. You introduce this matrix, and then you form the action by taking a circulation around the plaquette. So you need some ingenuity to do this. because with this definition you will have discrete analog of gauge symmetry, and the reason we really desperately need gauge symmetry here is that otherwise you generate all these monsters. With the correct discretization, it keeps all the monsters away.
The even theory still would be renormalizable, right?
Well, yes, but it will contain many coupling constants because you can have many different terms like that.
So
You can call that renormalizable. Normalizable means that all counted terms are of the same structure as the original.
But I think Grish is saying that suppose from the very beginning you introduce not only trace at mu square but this thing, and then you'll have a renormalization group equation for several. You have this coupling constant, and so on. So you'll have some running complicated flow. As far as I remember, I'm not quite sure. I thought about these things 30 years ago. You can ask the question also whether this flow, whether it's possible that the flow will eventually lead to the Young-Mills, and I think the answer is no, but I'm not completely certain. Okay, now we are returning to our problem. Clearly, by the way, the reason, once more, it's the reason is that the cutoff here for the problem is that the cutoff breaks gauge invariance. It's the same thing as we said in QED, that the momentum, this condition breaks gauge invariant. It should be K. It should be the condition like that, which preserves gauge invariance. That we briefly discussed. And same thing with gravity, of course. If you do anything stupid, you will be punished immediately. You cannot discretize some metric tensor by taking finite differences and so on. What you can do is to, and that's quite amazing actually, you can simply forget about the metric tensor completely and forget about coordinates completely. And you simply say, let's suppose that we have a random lattice. What do I mean by the random lattice? Let's talk about the square lattices. We glue lattice from small squares. So we have a certain number of these small squares, and we prescribe the rule how to glue them together. And the conjecture would be that you have many ways of gluing them together. So you glue, obviously, the link to the link, and you can form different lattices in this way. The conjecture is that summation over all possible gluing should be somehow equivalent to the integration over all possible metrics. Far from obvious. So let's proceed and see if it's true.
Are those supposed to be of the same size or whatever?
No. They are the same size in the sense you take, say, 10 million squares, and then you prescribe how to. So all the lattices will have the same area in the sense. If each square has a unit area, then we fix the total number of those squares. But I shall describe very effectively how to classify this and how to do the summation. We will actually sum over. There is one more thing, is that if you glue them randomly, you can have surfaces with different Euler character. We will actually impose the condition that the Euler character is fixed. Then you will get an interesting result. So how to, it seems very difficult to do, but in fact it is not. You first know it's not difficult in 2 dimensions. In higher dimensions it is very difficult, although people tried this using computers, of course. Here we don't need a computer. So let's go to the dual lattice. So with each square we associate, we imagine, as I told you last time, a spider sitting at the center of the square. And so you have, instead of this picture, you have a picture like that, etc. And gluing is simply forming a Feynman diagram, a 5-4 Feynman diagram. So the picture which you get is something like that. It's just the vacuum diagram for 5-4 theory. We clearly can go back and reconstruct the random surface. For example, this square will be glued, this side will be glued with this side, and so on. So different sides are glued. If they are glued together, they are just connected by the line of the Feynman diagram. And now we can actually see, we can count the number of Feynman diagrams very simply. If we simply count Feynman diagrams without thinking about topology, it will not lead to an interesting result, but still let's figure out. So what would be a very simple method to find the number of Feynman diagrams of a given order? Suppose we have this Feynman diagram, and there are many of them. How many? How to count them using what you know about functional integrals?
How many diagrams of this slide?
No. How many diagrams of a given order? It's this diagram, let me see, 1, 2, 3, 4, 5, 6. It's 6th order diagram of 5-4 theory. And I'm asking, suppose I want to know how many diagrams of 6th order there exist. Different, yes. And that's, again, looks like a complicated problem, but it's an elementary problem. Very simple. You just have to remember what's the relation between Feynman diagrams and functional integral.
It should be factorial.
You see, it will be more complicated.
Zero-dimensional integral.
Yeah, the key point, it will be factorial, yes. It's actually it's some
Right.
complicated expression with the gamma function, which we will derive, but asymptotically it is, of course, the factorial. But it's a zero-dimensional integral, so the propagator, let's simply say the propagator is 1, and we have phi to the 4th. So all you have to do is amazingly simple. It's simply the usual integral d phi from minus infinity to plus infinity. And you have e to the minus 1/2 phi square, and you have e to the minus lambda 0 phi to the 4th. If you want to phi to the 4th to the n, where n is the number of vertices, we just have to expand to the nth order, and we have to divide it by n factorial because all these vertices are interchangeable, and that gives you the number of ways it gives you the number which is equal to the number of final diagonals. You immediately see, if we look at the generating function, lambda to the n, we get integral d phi e to the minus 1/2 phi square minus lambda phi to the 4th from minus infinity to plus infinity. In fact, you have to take a logarithm of this expression. Why I take the logarithm?
If you connect it.
Yeah, if I'm interested in connected diagrams only. And this you can calculate easily. You immediately see, though, just by one look at this integral, you should be able to see that there's the number of diagrams blows up much faster than any power. How would you conclude from this expression that it's faster than any power?
This row is not convergent because you can change the sign of lambda.
Yeah, there should be essential singularity in lambda here, because if the integral with different lambda diverges, and so if you look at the saddle point, it's something like c divided by lambda, which you get, and that corresponds to this thing. Yeah.
Right now, doesn't these two lines actually coincide?
Which, oh,
If you
yeah.
took the logarithm.
Yeah, right. I should take in fact, to be the simple way to make it correct is this. But thank you, yes. There was, I have to carefully to divide 5/4 by the integral. I just don't. You see, I'm rushing because it's not the answer we are interested in, and I want to go to the. It's not the answer we are interested in because it includes all topologies together, and we need to get a meaningful answer. We need to separate topologies, just Euler characters. I remind you that in 2 dimensions, any surface has topology of a sphere with a certain number of handles, any orientable surface. And we want to start with a sphere, with a spherical topology. And there's a very good way to do it. And surprisingly, it gives the right answer. You see, it also tells you, as you see in this picture, there's no matrix, no metric tensor, no coordinates, no nothing. It's just purely geometrical. If we want some extra degrees of freedom, we can put it on this lattice. Actually, people did this, and for example, the Ising model on this thing is easily described, and so on. So the only thing is topology now, and that's important and simple also. To do topology, let's look at the diagrams not for the single scalar field like here, but for the Hermitian matrix n times n by n matrix, phi ij. Phi ij is a Hermitian field, and let's look at the following integral. The product of all this phi ij e to the minus. Now it's important to put the factors of n correctly, and I shall tell you how I'm doing this. It's phi trace pi square plus lambda 0 trace pi to the fourth. Now, what's the principle how I select this n-dependence? I want we will see from the answer that the contribution from with this normalization, when the action is of the order of n squared, trace is of the order of n, because you sum all sum over n values. So we want the exponential, the total action, to be of the order of n squared, and thus remember this general rule: if you make this choice, then things will come out in their natural scale. So you will see it in a moment. But just as a mnemonic rule, the action itself should be of the order of n squared, and trace is of the order of n. This rule is applicable in all cases, in much more complicated cases as well, like n equals here. So it's also what we will study now is the functional integral. Is this integral, what kind of diagrams we generate, what kind of surfaces we generate. And the answer will be that in the large n limit, we will get the surfaces with spherical topology. Let's very quickly explain this. We have the good trick for these matters is the so-called double line representation. First of all, you see that phi ij, phi kl, as you can read from here, is 1 over n delta ik delta jl. It's Hermitian field. So it's complex field, and it satisfies this condition. And so you have, and clearly the integral is invariant under unitary transformations. That will be important also in a moment. So you have this, the double line representation is that you have this for the propagator, and the propagator is 1 over n. Now let's look at some diagram, some particular diagram. I will choose, by the way, you also see that the coupling constant is of the order of lambda 0 multiplied by n. You will have things like that, diagrams like that. And lambda will be of the order, the coupling will be of the order of n. Let's look at the diagram like that, for instance, which I draw in this way. And in double line presentation, it will be something like this. It's sometimes called these things, mathematicians call them fat graphs. Let's decode it. Let's see what it depends on. Well, you see, it's all simple. You have propagators. You have two propagators, which gives you n minus 2. It's a contribution to free energy. N minus 2. You get the n from the coupling constant. And what do you think we get from the summation of over these guys? You see, when you have a closed thing, you have the delta symbol, which is equal to n, trace of the unit matrix, which is equal to n. So you have n from this phase, and n from this phase, from overall. So you get n to the cube. And as a result, you get the answer n squared.
The one where n is our propagator.
Yes, that gave me n minus 2 here. Yes. And now more generally, it's now extremely simple to evaluate n dependence. You have 1 over n from the propagators to the number of edges. You have n to the number of vertices. And you have n to the number of faces. You have face. There are 3 faces here, and the one coming from this. So, all in all, you have the formula, quite remarkable formula, n f minus e plus v. And this combination, I assume, is familiar to you. It is just the Euler character, which for a sphere, spherical topology, is equal to 2. And we indeed got n squared here. And the basic conclusion is that in the large n limit, only spherical topology will survive. We will have random surfaces with spherical topology. Then we will go beyond that, but let us start with this simple spherical topology when n goes to infinity. The question is how to calculate this integral. You see, when we had this integral, there was nothing to calculate. It's just trivial gamma functions. But the matrix integral at large n is something non-trivial. And people developed beautiful approaches to this. I will tell you what they are. But I want you to appreciate this big surprise which is here. We are doing something totally disconnected from our calculations with metrics, metric tensors, gauge fixing, logarithms, anomalous dimensions, and so on. We're doing something totally different, completely unrelated. And at the end, both things leads to the same beautiful mathematics, to the same answer. For example, the anomalous dimensions, I'm getting slightly ahead of myself, but as I said, with the previous method, with the Einstein-like method, you can calculate change of anomalous dimensions. For example, in the Ising model, anomalous dimensions, if I remember correctly, from energy density, which is 3 fermions, which has 2 fermions, it has dimension 1, and logarithmic specific heat, it becomes 2/3, and so on. So it's concrete and calculable in this way. And what is absolutely stunning is that we will obtain the same result from this discrete geometry. So that's to motivate you to follow this calculation. And how general it is, whether the same thing happens in higher dimensions, is still unknown. So the key idea to calculate this is to use the saddle point methods. However, it's not so simple. You might say, okay, it's very easy. You have a large n factor here. So you would expect you simply minimize this thing and that's it. What's wrong? It's wrong. It's far less trivial, as you will see. Why it is wrong? Why the saddle point method breaks down? Although we are really looking for the leading asymptotic behavior in n. But why usually we say if we have in the exponential a large parameter, we say that we can minimize it and then corrections will be suppressed by 1 over square root of n.
But it will be renormalized.
The what?
This parameter will be normalized by corrections.
Well, but what about textbooks, mathematics, which tells you that if you have some integral e to the large n multiplied by something, they teach you to take the saddle point correctly. And they estimate the error, and the error is indeed 1 over square root of n. Here, the error will be large. Why? Well, I'll tell you why. When the standard statement about the saddle point refers to the integral over one variable or several variables. In this case, indeed, if you have
the number of variables scales with this number.
Yeah, you got it. Yes, exactly. When the number of variables is of the same order as n, or even more than that, then you cannot. The naive method isn't applicable, and it's very clear why. Because you see, you try to calculate the correction to the saddle point, and it involves many n square integrals here. And you get the action, classical action of the order of n square, and quantum correction is of the number of these saddle integrals near the saddle point. And it's also of the order of n square. So that's not working. What is working is the diagonalization of this Hermitian matrix. Hermitian matrix can always be brought to the diagonal form by this transformation. And so you have you will parameterize it in this way.
so we would have n parameters instead.
Exactly. That's the point. The action, classical action, is of the order of n square. But if we manage to eliminate u and integrate over these eigenvalues, there will be only n of them. So they will be unable to compete when we calculate quantum corrections. And there is a small trick which actually mathematicians worked out long before, which is that going from integral phi ij, it's the integral over matrices u, the integral over lambda i's, and the Jacobian. Because you should look at it as change of variables. In fact, it's very close simply to change from Cartesian coordinates to polar coordinates. And this Jacobian, you can calculate it in many different ways. A good way, which I prefer, is I will not go through the calculation, although if someone is interested, I will. You take the metric in the fields, in the space of fields, and the distance in the space of fields. When you know the distance, you can reconstruct the measure. And this distance, it actually, when this is done, it gives you so it's the distance is the trace of delta phi square, and delta phi is it contains delta u lambda u minus 1 delta u minus 1 u plus u minus 1 lambda delta u, and so on. When delta u is infinitesimal, you reduce this metric. I'm going very schematically to the following. This metric, let's call it delta s square. Delta s square becomes delta lambda I squares plus when you look at these commutators, you will get the term lambda I lambda j omega ij square, where omega ij is the delta u minus 1 u is equal to omega. Anyway, in this way, you can calculate the measure, namely change variables from this to this. And what is convenient is that u drops from the action. The action is simply invariant under this. And I shall now write down the answer for the integral, and we will discuss it next time. The answer is that the measure, this is Cartesian coordinates, and the polar coordinates will simply be this is the Jacobian, which is calculated in this way. And multiplied by the unitary matrix, but nothing will depend on the unitary matrix. And so finally the answer for that, it's not the answer yet, we will have to calculate it, and we will, but that's the last formula for today. It will be v lambda i's e to the 1/2 lambda I square plus I should have called it g G0 lambda I to the fourth multiplied by this lambda I minus lambda J square. And tomorrow we will quickly, it's not, it's actually we're pretty close to the end. We will calculate this integral. It turns out in the large n limit it can be done because now you can use the 7-point method, and we will see that it produces these correlation numbers obtained from the totally different direction. Okay, let's stop here. Excuse me? Oh, yes, right. That's important. There's n, and that's. But this time, the difference, the great difference is this time you are allowed to use the saddle point method, provided that you include this term. And this term is of the same order because, as you see, this term actually is, it's convenient to put it, it's the sum 2 log lambda I minus lambda J. So it's like a logarithmic and Coulomb interaction between the particles. It's quite fascinating that these eigenvalues they are responsible for summing over random surface with fixed topology. Okay, so let's stop it.